Thank you, and hello everyone. So today I'm really just going to be presenting the work that I did during my PhD dissertation, which focused on the storage, ascent, and release of silicic magma at the onset of 3 different caldera-forming eruptions. This work, of course, was in strong collaboration with my PhD advisors, Paul Wallace and Colin Wilson, as well as Elliot Swallow, Jim Watkins, and Ying Liu. To start off today, I just wanted to discuss the kind of standard model for caldera formation, which was presented in Cashman and Giordano in 2014, kind of reviewing how do we look at caldera-forming eruptions. Typically, we have previously kind of envisioned these large vats of magma that sit within the crust that are long-lived systems. They tend to be stratified in our views with either volatiles, composition, or crystals. We then typically have some sort of central vent eruption that is driven through overpressure within the chamber, leading then to finally, after enough magma has been evacuated, that you then have caldera formation. However, like any good model, you mostly are using this as a stepping stone to then argue against aspects of it, where many people, I think, now agree that we don't really see this very often or ever in the systems, that things are melted, stored in these mush bodies. But really what I want to focus on today is the second point, which is eruptions begin with central vent overpressurization. Currently in the caldera community, there's a debate as to how large volume eruptions are triggered, where traditionally we have thought of them again as these chamber-triggered events due to volatile exsolution or recharge overpressurizes the chamber, leading directly into the caldera-forming event. However, there have been a growing number of researchers that argued that these large volume systems behave differently, that they cannot be triggered through overpressure in some cases, but rather need failure of the caldera roof to initiate the eruption. Others have shown evidence that tectonics could be influential at the onset of some of these eruptions. The challenge, however, is that much of our understanding for the initiation of these systems comes from numerical and analytical modeling, where we really don't have a lot of other ways of distinguishing which of these 2 different methods might be applicable in any particular system. Additionally, we often envision this as a continuous process where you have your initial eruption that leads directly into Ingenbreit formation and then caldera collapse. However, the question is, well, what if there were eruptive pauses? What if these eruptions continued and stop-start several times? What would this look like, and how would this affect the modeling of it? Additionally, what if there were multiple magma bodies within the crust that were being activated, or multiple vents at the onset of these eruptions? This is something that currently most numerical models, likely due to the complexity of it, really don't take into account, but would really change the timescales of how these eruptions begin. And most importantly, the question that our group really has been focused on trying to answer is what evidence can we use to recognize and quantify these sort of complexities at the beginning of these eruptions? And hopefully, from what I show you today, you will see that we think that we're getting closer to some ideas for how to integrate methods for coming up with some answers to these questions. The approach we took was to look at 3 different supereruptions where there is field evidence for contrasting beginnings. So these 3 eruptions include the Bishop Tuff, where fall deposits led directly into Ingenbreit formation, where both were coeval at points. So this is really our best example of a continuous eruption. The Huckleberry Ridge is a part of the Yellowstone volcanic system. It's the oldest of the 3 caldera-forming eruptions. And what we see at the beginning is evidence for small-scale reworking in terms of what you see here, cross-bedding, as well as interaction with rain. And these have been interpreted as multiple pauses within deposition on the order of days, potentially weeks. Of course, this is challenging to quantify, but this is all the work of Colin Wilson's fieldwork, suggesting that there was start-start behavior over and over again at the beginning prior to Ingenbreit formation. And lastly is the Orinui eruption, which is kind of the other end member from the Bishop Tuff. It's broken into 10 distinct phases, where eruptive pauses are inferred to have occurred between 5 of those phases. The longest is between phase 1 and phase 2, which is thought to be in the order of months, because you see substantial reworking at the top of phase 1. Interestingly, the first 2 phases of the Oronui eruption are also associated with a foreign biotite-bearing magma, which is thought to have been laterally injected along a rift zone and is from a magma source that's about 15 kilometers away. The question then becomes, do these field-based interpretations reflect differences in the decompression history and the opening timescales of these eruptions? Of course, the rate at which a magma ascends is a challenging question and is an important one, as several researchers have suggested that this rate is directly linked to the overpressure within the system, which might allow us to get at what the state of these magmatic systems were at the onset of their eruptions. However, it remains challenging to quantify these timescales in silicic systems. You need some kind of recorder that can react on the timescales of magma ascent. Where traditionally things like hydrous mineral breakdown rims or microlake growth, which have traditionally been used in more mafic systems, can give you this information, these things behave too slowly within silicic systems to be quite useful. Other people have used bubble number densities to try to get at decompression rates within silicic systems. However, these have been found to be somewhat skewed to the fragmentation threshold and are thought to be too fast. So the approach, and then again, much of our understanding really then for these silicic systems has come from numerical modeling. So really we are trying to strive here to find other ways to get at these timescales. And the way that I have been approaching it is to use volatile concentrations, so namely water and CO2 concentrations and their gradients to quantify the timescales of opening behavior. The benefit of using these 2 volatiles is not only do they react on timescales of magma ascent in silicic systems, but they also are pressure-dependent species, meaning that we can integrate our timescale and decompression information with where things are situated within the crust and ascent towards the surface. My talk today is broken into 3 parts. So the first part is going to be kind of the bulk of it, which is going to focus on the Huckleberry Ridge tuff. I'm going to introduce you to the 2 methods that I've used throughout my dissertation, the volatiles and reentrant one I'm also going to be using here for my postdoc, and also show you some of the geochemical evidence that we have for some complexities in the system. I'm then going to apply this hydrogen diffusion through quartz method to the Oronui and Bishop Tuff eruptions to try to say some kind of broader things about the triggering of large caldera-forming eruptions. And finally, show some of the recent work we've been doing looking at final ascent rates in comparing all 3 super eruptions. So to start out with, here is just a map of the Pacific Northwest, so the northwest part of the United States. And Yellowstone is currently the last kind of manifestation of a hotspot track that makes its way along the Snake River Plain and had some complicated beginning that we continuously debate, including multiple kind of locations for the flood basalts. So Yellowstone, again, is located over here. And the Huckleberry Ridge tuff is the oldest, at 2 million years old, of the 3 caldera-forming eruptions that have formed the Yellowstone volcanic field. It is by far the largest of the 3 at 2,500 cubic kilometers worth of material, where the fall deposit that I'm going to be focusing on today is thought to be 50 cubic kilometers worth of material. So this is a massive eruption. It's actually broken into 3 different ignimbrite members, but we're just going to be focusing on the fall deposit that occurred prior to ignimbrite emplacement of HRT-A. So here is the area that was mapped by Christensen in 2001, and Colin Wilson has been spending the last 15 years essentially working to improve this map, which will come out hopefully one day. And here is the extent of the ignimbrite field. Here's the outcrops that we have for ignimbrite localities. And this star represents Mount Everts, where we get this beautiful fall deposit that leads right up into hot ignimbrite. The evidence for time breaks is right here at the base of this fall deposit. So we sampled throughout the time breaks as well as up through the more steady portions of what is inferred to be a more steady column. From this, I was mostly focused on sorting out quartz grains and then looking for melt inclusions, as well as reentrance. So I know most of you know this, but melt inclusions are essentially little blobs of melt that are entrapped within a growing crystal. So this is an example of an olivine, and right here would be an example of a melt inclusion that grew in a melt that represents that time period in that crystal's growth. However, reentrants, which are also referred to as embayments, are open to the surrounding melt, meaning that they can diffusively re-equilibrate and record a changing composition per se. Let's say this crystal moved significantly from where it was originally crystallized. The reentrant will record that. The two methods that I'm going to talk about today, the first one involves hydrogen diffusion, which can occur through the quartz lattice on the timescales of days in rhyolitic systems. So although these melt inclusions are isolated, hydrogen can move as well as lithium through the quartz lattice. These are shorter time or longer timescales than in mafic systems, which this can occur on the order of hours. So an interesting tidbit. And the second method is looking at water and CO2 gradients that form in these reentrants during magmatic ascent. And that's because water and CO2 will go into a vapor phase during decompression, and this reentrant is going to strive to try to maintain equilibrium, and we can then model this profile to come up with an ascent rate. So this is a simple schematic that many of you have probably already seen, but I think is kind of important for understanding what I'll be yammering on about. And so when a melt inclusion is entrapped in a reentrant in a crystal sitting in the storage unit, a storage reservoir per se, it's going to have a water and CO2 concentration that falls along an isobar. However, during magma ascent, so as bubbles start to form, and perhaps let's say this material stalls in the system, you're going to have a degassing path, and these reentrants are going to re-equilibrate along a degassing path. So first losing CO2, and then water. However, your melt inclusion can only lose hydrogen through the quartz lattice, which will shift values over left while maintaining their CO2 concentration, so long as there's no vapor bubble, which there are no vapor bubbles in any of the huckleberry melt inclusions. We then, after doubly polishing about 150 quartz grains and measuring them for water and CO2, we measured them for major and trace elements, which is how I'm going to start the presentation. So the first geochemical plot, exciting. So here's rubidium versus chlorine and uranium. Simply, these are incompatible elements within the crystallizing assemblage, meaning that during crystallization, these values are going to increase. So each diamond here represents a melt inclusion, and each color represents a single layer that we sampled at. So just looking at it first, these are all high silica rhyolites. We have 9 different layers. The first erupted layer, MM11, seems to be the most evolved, has the highest water concentration, and the upper units seem to have the least evolved compositions. So from first look at this system, it really looks like your typical stratified system, first stuff out, most evolved. However, we were really surprised to first see that when we looked at trace element concentration, so especially barium in this system, things started to cluster and not produce a continuous fractionation line. They even fell on different fractionation lines. To try to determine whether this was a statistically significant observation, geochemists dove into statistics, which was fun. So by using several different major and trace elements, we were able to use a statistical program to show that we had 6 statistically distinct quartz populations crystallizing in this system, which on any one geochemical plot, you can't get all 6 to show. So in this case, this plot, even though they're overlapping in compositional space, have very different CO2 concentrations. So they couldn't have been in the same physical space when they crystallized. The complexity, of course, continues when we now look at how this is restored pressure, so using the water and CO2 concentrations versus rubidium again. what we notice is that MM11, that quartz population 1, is actually one of our deepest crystallizing units, whereas that least evolved unit is actually one of our highest crystallizing units, meaning shallowest units. So again, this is kind of, yeah?
So when you did this cluster analysis, did you use the concentration or did you use the ratios?
I use the concentrations.
Okay.
Yeah. So you can do like an invariant plot to try to figure out which ones are like distinct traits. So we use CO2 and chlorine and calcium, barium, etc. And then did like a cluster analysis to see which ones were most statistically like each other using all of those.
Sorry, what's the error on the pressure?
What did you say?
What's the error on the pressure?
The error? Well, the error in the pressure is going to be associated with the error in the water concentration, because the CO2 concentration, our error bars are quite good with the FTIR, like usually plus or minus 20 ppm, so that's going to barely shift this. But with, as you'll see soon, there's a wide range in water concentrations that we had to restore. So I would say that the error might be on the order of 100 to 200 bar, but not enough to collapse those. No. Yeah, no. I mean, these are drastically different CO2 concentrations in the huckleberry. So this system, these have about 800 ppm CO2, and these have none. So it's like very hard to argue with the CO2. All right, so here's the same plot of just now barium versus strontium and the different little clusters that we have. But as I mentioned previously, after entrapment, this quartz crystal in this large vat of magma might move and change compositions. So we then compared these same barium versus strontium versus reentrants, as well as obsidian pyroclasts, which were co-erupted, or little shards of melt. And what we see is that only 3 of the original populations, although they're still present, have collapsed, and we no longer see any evidence of some of these other melt groups. And we take this to suggest that the melt diversity from the inclusions went from six distinct crystallizing bodies into amalgamated into 3 different melt groups that were then erupted. But the important thing to kind of recognize here is that Elliot Swallow then did, who is a PhD student with Colin, then went through and did a lot more work on the obsidian pyroclasts and found that no single pyroclast had a composition from any of the 2 groups in the same class. So we're taking this as evidence of suggesting that these melt bodies remained separate upon their evacuation and never were mixed within a conduit system. All right, so looking at how this melt diversity relates to the outcrop, we see that as we go up from the base, so it's going to start over here and then go up. And so these are just pie diagrams which split up how many of these different quartz populations exist. And we do see some pretty coherent trends within the quartz populations where we start with purple and really don't see it very much except for a minor component. Then it goes to these greens and blues, and we have these 2 kind of shallow melt bodies that are coming out at the end. But again, when we know that that isn't the melt composition at the end, so looking at what the obsidian pyroclasts and the reentrants show us, we see again, this purple only coming out at the beginning and then essentially is absent from the entire fall deposit afterwards, suggesting this is a very minor component of the melt composition coming out. It then transforms into this blue, and then blue and green seem to be co-depositing at this point, and then it turns into the majority of the deposit being this green composition.
So you haven't shown the ground mass glasses. Are they the same as the reentrants?
Yeah, that's Elliot's work. I'm going to show you some of Elliot's work in a little bit. But yes, the glasses also do the same. The obsidian pyroclasts are kind of thought to be representative of that ground mass glass. They look like obsidian, but they still have CO2, and we're taking those to also represent it. It's also in feldspar. So the kind of take-home point from this section is that we see this coherency throughout these compositions throughout the fall deposit, where they're sequential as well as coeval. And so we suggest that we have 3 separate vents at the onset of this eruption that are active simultaneous, and then this one shuts off, and then we see 2 simultaneously depositing before this majority one takes over. All right, switching from the chemistry that we just observed, we're now going to look at some of the faster diffusing elements in this system. So again, these are all the different layers, and these are all melt inclusions. And what we notice here is a significant amount of scatter when we look at lithium concentrations and water concentrations in these melt inclusions. And this is so much scatter you can't even really draw a line through it as a geochemist, even though I did, but forgive me. So this highly scattered pattern is suggests a more complex relationship occurred post-entrapment, that there was exchange with these quartz crystals with the changing surroundings. In lithium, we really don't understand the behavior very well of how lithium behaves within an exolved gas phase. However, we do have a very good understanding of water concentrations. So I'm going to focus on water now. So here is a water CO2 plot. And what we'll see is if we look at any one layer, we have a range in water concentrations for relatively homogeneous CO2 concentrations in almost all layers that we observe. And it's quite a range from 1 to 4.5 weight % water. The first thing to kind of note is that this is a really surprisingly wide range of concentrations of water in a rhyolitic system, probably one of the largest we'll ever really see in these systems, and this is typically more observed in basaltic systems. So when we first were looking at this data set, we were trying to figure out exactly how we could have, in the same layer, melt inclusions that went up to what we're inferring to be storage, co-erupted and co-mixed with inclusions that had really low water concentrations, and essentially a whole range preserved in each of these layers. So we infer this range to represent diffusive loss of hydrogen due to slow ascent towards the surface, but we really didn't have a very good understanding of how we could have all of these co-erupted. And really the breakthrough came with looking at this study by Rutherford and Hill. So after the explosive eruption of Mount St. Helens on May 18th, 1980, all during that summer there was dome growth that was occurring in the top of the crater. And this dome growth was then followed by these punctuated explosive eruptions. So what Rutherford and Hill did was to look at individual pumice clasts from all of these explosive events and look at the thickness of amphibole breakdown rims, which is a breakdown reaction due to being in the presence of a lower water or a lower pressure system. And what they noticed, so taking just for instance October 17th, so the dark color, which is a little easier to see, they found that within any single pumice class, they'd have essentially amphiboles that had no breakdown rims co-erupted in the same class with something that had experienced 7 days at lower pressure and up to 16 days at lower pressure. The way they explained this data set was to suggest that the things that had spent the largest amount of time at lower pressure had been ascending slowly towards the surface to be feeding this dome activity. And then these punctuated eruptions would come up and mix things that were going at different times in the conduit system into a single pumice eruption. So this kind of gave us an idea, well, maybe something similar was happening with our data. And what this would look like would be that you can imagine this as being your storage container, and this is your ascent towards the surface. And the longer amount of time that you spend within your conduit system, especially the shallower you go, or if you stall in the system, you're going to be in contact with lower water, meaning you're going to diffuse your water and have a lower water concentration, or you're going to form a thicker amphibole breakdown rim. You then would have some sort of punctuated eruption, which then allowed material that had been essentially at storage to co-erupt and mix with material that had spent a longer amount of time within the conduit system, which suggests that in any one fall layer, we have a range of decompression rates and histories being recorded by every single, essentially, quartz grain that was erupted in these single pumices or in a single layer. We can then try to determine how much time this then equates to by using a 3D diffusional model that was first developed by Chin et al. In 1992, and then Liz Cottrell, who was just here, actually refined it in 2005 into MATLAB. Using a diffusion coefficient, which is constrained just currently through experimental data sets, partition coefficient, and then most importantly, well, not most importantly, but the size of the inclusion and the distance to rim are huge factors in this, where smaller inclusions and the ones that are closer to rims are going to lose water quicker. We also need to have an estimate of the initial water concentration, which is big since most of our inclusions have it, we believe, experienced diffusive loss, and an estimate of what the exterior water concentration is, to then determine how much time it would take to go from what we think it began with to what we measured. In this plot, I'm just going to show you one of the ways that we did this. So here is each of the different stratigraphic layers. What we see again is this range in water concentrations being preserved in every single layer. We can infer that the starting magmatic concentrations are the highest concentration in any particular layer. You can also use a relationship with another incompatible element like rubidium to restore what the original water concentration was. But in either way, we're getting values that are quite similar, and it's probably not our biggest error. The larger uncertainty is determining what the external water concentration was. In our models, we're just assuming that it wasn't constantly changing like during an ascent model, but instead we're putting it in context with what our best estimate for the external melt was and then determining how much time that represented. So in this case, it's just set to what the lowest melt inclusion concentrations were, which will give us our fastest ascent times. Essentially anything that is up, so another way that we've done this is using the reentrance interior for an estimate of the water concentration from each layer, and that will just serve to kind of prolong the times. So what this is saying that if you started with a 4.5 weight percent melt inclusion, it will take you about a day to get down to 3.7 weight percent, 5 days to get down to 2.7, and 10 days to get down to something around 1 weight percent.
How much water is in the ground mass class?
In the ground mass glass, well, essentially, it's around 1 weight percent. We did all the obsidian pyroclast, so I think it's not a bad estimate, but we did, for the paper, use reentrance as well, because in theory, in this model, we don't really know if they stall or if they're slowly ascending or if they're stuck at different portions. And it does make a huge difference on the time. But we're really not going for precision, we're really just trying to get an estimate of how much time is being represented.
So just to be clear, so you are putting this inclusion in a relatively dry magma within 12 hours and then see what happens or something like that. You don't do this gradual.
I don't, no. I do that for the reentrant models, but we haven't done it here.
Okay.
So all these times would get longer.
Yeah.
But there's too many uncertainties at the moment to do that, I think, and feel very confident. So probably not surprisingly, but the majority of the inclusions from the Huckleberry Ridge have experienced some amount of diffusive loss, where most of them require timescales between less than 12 hours to 5 days. So this in itself is kind of a new look at how these eruptions can begin. This is a lot more time than we, for instance, in models predict that material is going towards the surface. And it's something that is consistent, most importantly, in every single one of these layers. And as we have seen from the reentrance and the obsidian pyroclasts, these are representing 3 separate vents, we believe, and suggesting that a similar history is being reoccurring within this system with every single one of these explosive episodes. And this area down here is where we see evidence for time breaks from reworking in the system. So overall, we see a complex and surprisingly sluggish ascent at the onset of this eruption, but we see consistent ranges and timescales preserved in all 3 of our final melt populations. And so we've taken all of this together to suggest that an external control, or perhaps the roof of this system, was really important for understanding how this material was coming towards the surface. So switching gears a little bit, we then used reentrance to try to figure out the timescales of that final punctuated explosive event. So this is a relatively new technique that really hasn't been applied in rhyolitic systems yet. It's mostly been applied in, well, it was applied for Mount St. Helens and then 2 basaltic systems. So again, during decompression, gas is going to form bubbles. It's then going to drive decompression, which then allows us to make measurements and model the decompression rate. What this looks like in the system, so if your reentrant is sitting down here somewhere in the chamber, it's going to have a homogeneous water and CO2 concentration, And then here, these are actual FTIR measured points. So during ascent, the boundary condition is going to drop. So in this model, again, we are updating at every decompression step for what the external concentration is going to be. And so if you use a high decompression rate, you're going to produce a profile that looks like this. So this is a 4-minute ascent rate. The best fit for this system is 32 minutes. And then this is what would happen if we continue to let it go. At one point, these reentrances will re-equilibrate. And they tend to re-equilibrate in less than a day. So they're very quick at re-equilibrating within the system. So if they stall, for instance, in the chamber, something we're going to probably talk about in a little bit, they will re-equilibrate quite quickly. The assumptions that go into this model are the starting conditions. You can either use the melt inclusions or the interior of the reentrant, the initial exhaled gas, the fragmentation threshold, which we just set to be 10 megapascals for right now. And this is when quenching is assumed to have occurred in the system. This uses constant decompression, which is something I'm going to get back to at the end of this talk, and isothermal ascent. So these are all assumptions, but kind of the best we can do at the moment.
Speciation?
Speciation?
Low water?
Oh, you can look at speciation. Yeah, we do that.
That's changed the diffusivity.
Oh, well, it's the molecular water that changes the diffusivity, so you can put the molecular. We do that in the calculation. Yeah. So we were able to look at 10 reentrants through the fall deposit, which gave ascent rates between 0.35 and 7 meters per second, which then translate into 1 to 2 hours of a final ascent in the conduit. So this would be the rate at which those final explosive eruptions are coming up into the system. And importantly, these rates would be associated with the melt inclusions that have experienced essentially no loss in the system. So the melt inclusions that we believe are going back to storage would be coming up in this final explosive, this rate of an eruption. Comparing these rates to other systems, mostly Mount St. Helens, which has had a lot of work done on magma ascent rates, what we see, so large Plinian eruptions, here's the melt inclusion decompression range, so in meters per second, and here's the reentrants. So the upper portion here are the reentrants that essentially are overlapping with melt inclusions that have experienced no loss. These compare with the preliminary study that was done by Liu et al. On the Oronui. However, are slower than estimates from Mount St. Helens, the Plinian phase, and Fuego, which used the reentrant method, which was a little surprising initially. I think a lot of people thought that at the onset of one of the largest eruptions on Earth, you would have faster ascent rates than you see within these basaltic systems. But from the study that I will show you at the very end, it seems like these are very much the range that we're getting, so they're not getting faster. But this one, I think, is too fast. And then the melt inclusions that have experienced, I could go into it if you want to, but there's some issues with that study. Anyway, the melt inclusions that have experienced the most amount of time within the system are actually quite comparable to the dome growth and explosive events that were found in the Rutherford study. So to conclude the Huckleberry Ridge Tuff section, just to build a nice conceptual model so we can have a schematic to look at, we have 6 quartz populations that we believe have amalgamated into 3 melt bodies at the ends. These melt inclusions from these bodies suggest highly variable decompression histories on the orders of hours to days, where these final ascent rates are all on the order of 1 to 3 hours. These slow ascent rates seem to be very similar to the summer 1980 Mount St. Helens eruption, which suggests perhaps low overpressure within the feeding body system. And such behavior together, taking together the start-stop eruptions, the multiple vents preserving similar time histories, and the fact that we have this sluggish ascent behavior, we're taking this to suggest the possibility of an external control being important at the onset of the Huckleberry eruption. And considering that multiple fault zones intersect with the Yellowstone caldera, we have created a model by which the intersection of perhaps one of these fault zones with a topographically perhaps quite complex magmatic systems where we have isolated melt bodies that seem to erupt from separate vents was kind of how we are envisioning the onset of this eruption. Now, Elliot Swallow is Colin's PhD student and is going into more detail into this eruption. So he looked at the matrix glass and feldspar populations through the fall deposit and into the ignimbrite. So he went in the ignimbrite. And what he sees in the fall is again the same 3 distinct bodies, which are also shown as different actual populations of feldspar compositions. But initially, that the majority of that melt body, that last melt body, was going to dominate when we got into the ignimbrite. But this is the plot of what he has seen for the ignimbrite. It has a huge range in barium concentrations. And again, we see clustering of different compositions, suggesting that we have not only the original 3 melt bodies, but that we're tapping into 5 additional clusters as we get into the ignimbrite. And there seems to be no rhyme or reason as to how these things are evacuated. He looked at ignimbrite from surrounding the entire caldera, and there's no organization, it appears, in how these things were evacuated. Thinking about how this fits into the standard model, with this paper, they suggest that maybe silicic systems are becoming a little bit more like mafic systems, and that we might have sills that are kind of feeding off of each other when one erupts that then changes the stress regime or pressure history of the next. Although in this one they have it coming out of a single vent, and we are arguing here that we have multiple vents in these systems that are being activated. All right, so just real quickly, I promised that I would talk about 2 other eruptions. So I'm going to show you the water and CO2 concentrations from this and briefly touch on diffusion of hydrogen in these 2 to make a kind of a larger scale comparison. The Bishop Tuff is a more modest eruption at 650 cubic kilometers. It formed the Long Valley caldera, which is located in eastern California, and started as a point source that then unzipped along the caldera rim. Again, fall activity goes directly into flow, where Colin and Hildreth have estimated that the entire eruption took around 6 days to come out from the continuous behavior that they saw within the flow and fall deposits. In contrast, the Oronui eruption, there are 10 different phases where we see the longest time break between the first 2 phases, which is also associated with a rifting event. So this is from Aidan Allen's PhD thesis, where they see within the first 2 phases these biotite bearing magmas that are associated with the dome system up here that were, they believe, laterally injected along this fault zone that connects the 2 systems, suggesting that rifting was important for facilitating these first 2 eruptions. So where I came in was, of course, to prep a lot of melt inclusions. And so we looked at, again, you've seen this data from the Huckleberry Ridge, where we have a wide range from 1 to 4.5 weight% water. In comparison with the Bishop, so this includes data also going, I looked at the first 2 fall layers, and this also includes Roberge, which goes all the way up into F9. And we see what's a little bit more common in a silicic system where the range is predominantly between 4.5 and 6 weight% water. So there is some water scatter, but overall, this is a more commonly observed feature within these rhyolitic systems. Now, looking at the Oronui, one might argue that it's somewhere in between. So it looks like we have water ranges between 3 and 6 weight%, which is most predominant within phase 1 and phase 3, where phase 2 is actually a little bit more homogeneous in its range in water concentrations. And both phase 1 and phase 3 are actually the first eruptions out of their vent site, so that might have something to do with their water loss ranges. So what we did, just to kind of give you the results of this project, is to then do the essentially the same model to all of the melt inclusions and give times to every single one. So we have about 50 from the Bishop, 100 from the Oronui, and 100 from the Huckleberry. So what is shown here is melt inclusion diffusive loss time on the x-axis versus relative abundance. And so this shows you how the kind of the probability of a melt inclusion falling within any of these regions are. So for the Bishop, which is kind of shown here, the majority of the melt inclusions that we have fall within less than a day of time within the conduit system, where 60% of the values show absolutely no evidence for diffusive loss. In the Oronui, only 40% show their original values, and then the Huckleberry, only 10% show what their original values were. But importantly, both in the Oronui and the Huckleberry Ridge, we see these diffusive tails, which represents this 1 to 5 days ascending in the conduit system. So taken together, the prolonged descent that we observe in the Oronui and the huckleberry has these diffusive tails and these low storage concentrations, together with the evidence for start-stop deposition within the initial fall deposits, we believe suggests that low overpressure was important at the beginning of these eruptions and perhaps indicative of an external control, suggesting that these eruptions may not have started without the aid of an external control until more overpressurization occurred within the system. All right, so the last thing I want to talk about today is the work that we've done to kind of improve and apply more readily this reentrant to reentrants everywhere, including Santorini. So the first thing we did was to convert the Lewidol Fortran code into MATLAB and then add in a best fit function, which allows us now to cycle through all of the important parameters and then use a chi-squared test to pick which set of parameters gives us the least error in best fits to our profiles. This was then applied to 31 different reentrants, which literally doubles the number of reentrants out there. So that's cool, and overall gives us a huge range in ascent rates, so spans over 2 orders of magnitude, which I like to optimistically think means that we can learn a lot about the huge range in system ascent rates, but is quite a large range from 0.1 meters per second, which is mostly shown by the early Oronui, all the way up to 15, which is from the Bishop. Now, a clever friend of mine helped me make this more real for you. So, thinking about how quickly this means things are coming to the system, we're going to use animals. So 0.1 meters per second is apparently how quick a baby squid moves through the water. A cockroach, fun fact, will move at 1 meter per second as it runs away from you, which is where a lot of our data falls. The fastest man in the world runs around 10 meters per second, so that is getting close to the Bishop Tough as running towards the surface. And finally, our hero here, the Patras monkey, is about the rate of the fastest ascent rate that we measured here, where the majority of our material is somewhere between a cockroach and a human. So imagine, that gives you like a real image of how quickly this material is coming to the surface in time scales that would take, I mean, you would have to run this fast for like an hour, so that'd be exhausting. But so anyway, comparing this to where most of our information comes from, which are conduit models, we see that really the estimates from conduit models range from 5 to 30 meters per second. And so the only reentrants that we measured that overlap with those are from the Bishop Tough, where most of our data points fall lower than that. Another proxy is bubble diffusion, so how quickly water can diffuse into a bubble and form a bubble during magma ascent, which overlaps quite well with our data set, which I think it should because they're really based on very similar premises. But really, we do have a lot of data points that are lower than what was previously kind of expected. Kind of interesting observations to make. The slowest ascent conditions that we have found are in the first 2 phases of the Oronui, and these again are the phases thought to be initiated through rifting, suggesting perhaps low overpressure within the feeding body. Whereas the fastest rates are from the upper portion of the Bishop Tough, which is the only eruption where we're really able to get far into the eruptive sequence because it's the only eruption that has fall deposits that are nice and glassy and quenched that are through the majority of the eruption. So the last point that I want to make today involves a really interesting observation, which might not look it now, but it will. So if you take the interior water and CO2 concentration and then you calculate a pressure based on that interior water and CO2 concentration from that reentrant, what we see is that the majority of them, all but a few up here really, fall away from the melt inclusion storage region. So this is what we inferred the storage, where everything came from essentially. So if you're really clever, like Paul is, and you say, well, just ask the simple question, why? It made us think, well, why do they seem to fall off over to the side? And so the model that we kind of came up with is that initially they have to have concentrations similar to the melt inclusions. However, their gradients seem to go and plateau to a lower water and CO2 concentration, where in that now best fit parameterization, we see that the reentrant interior does a better job fitting the profile in all but 4 reentrants, so for 27 of the reentrants. What we think this suggests is that the reentrants are actually recording an initial slower decompression phase where they're moving through the conduit system and are actually given enough time to fully re-equilibrate with the surrounding melts, prior to what is then the final kind of punctuated explosive event, which gives timescales on the order of 1 to 3 hours. This brings up 2 important points from the reentrants. The first is that the assumption of constant decompression from the storage region is wrong, at least in these systems, which is not that surprising. It's even in basaltic systems been shown that they need at least a 2-stage ascent behavior, which is essentially what this shows. But luckily it's more complicated than that, where the ascent rate is probably evolving much more like conduit models. However, we haven't really gotten to the point of including that in the code. And the second important point is that the reentrants are also recording the sluggish beginning that we're seeing in the melt inclusions, where if we start to apply a model to calculate how much time it would take to do constant decompression versus step function, you start to get at the timescales of days that we see from the melt inclusion population. Finally, going back to this last plot, what we see, especially in the Bishop Tuff, is that reentrants seem to be going closer towards those magmatic storage regions, which I believe suggests the removal of the initial slower decompression phase being important within this system, and perhaps the full connectivity of the conduit system being reached by this upper portion, where caldera formation is thought to occur right around here in the Bishop Tuff. All right, so in conclusion, the implications for the onset of these eruptions. From the Huckleberry Ridge, I showed that we believe that we have multiple melt bodies and multiple vents active at one time, changing the way we kind of view these systems. This is also being seen in more and more systems where clustering of data points are suggesting these kind of lenses of crystallization. We see sluggish starts in the Bishop and the Oronui eruptions through hydrogen loss. These are both eruptions where we see depositional breaks, which we're taking to mean perhaps evidence of an external control being important at the onset of these eruptions, but also importantly suggests that there's more time being preserved at the onset of these eruptions than we previously have given them. And finally, reentrants, I believe, are going to be able to be used to track how the evolution of a conduit system begins and how it evolves through a system if you can get a good sequence. And really in these systems requires a multi-stage decompression, which is something hopefully we'll start to work on. So that's it. Thank you.
Merci beaucoup, Madison. Des questions?
Have the timescales of the rim of hydrogen phases, like Amphibola biotype, been compared to the proton loss timescales for a single sample?
We don't have amphibole in any of these systems. Biotype's going to be, I think, a little harder. We haven't compared it, no. I mean, if it can react in the same timescale in silicic systems, I mean, the amphiboles that we saw were reacting on timescales of weeks, and those were in more
It seems to be comparable.
hotter systems. Well, it's comparable, but they're at different temperatures, so they're not comparable. So if you slow it, I mean, if you cool it 100 degrees.
Nobody has done this before?
No, not yet, but nobody's really done what I did before either, so.
Well, proton time.
Next step, you can do it.
Oh. I'm preparing retirement.
Yeah.
Have you considered analyzing for deuterium for your first method, just to get a better idea of the diffusion of
Yes,
hydrogen?
definitely. We did. We talked about that. Glenn and I talked about that for a while. Currently, there is a lot of uncertainty in quartz right now. We don't know how hydrogen diffuses through quartz, so Glenn is actually putting in a proposal right now to try to study it, and I think we'll actually use some of the melt inclusions I have to constrain that. So it's a goal. I think it's an important goal, but we don't know a lot about hydrogen in quartz systems right now. I think people haven't thought about it yet.
It hasn't been done before, like the, modeling or figuring out how it moves.
No, people thought it didn't move. Joke's on us. So.
so your phase 2 of
Yeah.
re-entry profile.
Uh-huh.
I think it can be interpreted as a cooling. So,
Oh.
so that you have a diffuse equilibration after the eruption of the cooling.
Oh, yes, yes,
Have
yes.
you
You could interpret it that way, but it's going to... So the problem with that is that CO2 is not going to diffuse that quickly. So if you have both CO2 and water, which we do for at least all of the Huckleberry systems, you won't produce a gradient within the CO2. We do see actually evidence, so there were 7 reentrants that were kicked out, and most of them were because the water had actually flattened. And I think that was due to the fact that the hot ignimbrite was right above them. So this was like an upper bishop and upper huckleberry. And so you can discern between the two, but it's probably something that's very important going forward to be able to quickly discern between them. Question?
So how sure are you of these 2 stages then? Because, I mean, you could do it in one stage, couldn't you, just by progressively depleting the inside.
Yeah.
Then the question is, statistically, how different is your 2-stage model from a one-stage model?
The 2-stage
You
model is
didn't show the
essentially
one-stage
just like if you assume it's something like this, right?
Yeah.
We're just drawing 2 lines.
Well,
So
it's going to go down. You're progressively going to deplete the inside, aren't you? So.
Oh yeah, but I'm saying that like if you model it as ascent all the way from the bottom to the top, you're going to have it really slow to be able to re-equilibrate. CO2 re-equilibrates, if you, let's say you moved it from like here to here, it's going to take 18 hours for CO2 to re-equilibrate. So you either need to let it sit there and re-equilibrate, or you need to move it slowly enough that it can re-equilibrate by the time it gets there. So essentially, no matter how you slice it, you need to have something very slow to begin and something very fast at the end, and then you could probably do a range in between, like honestly. You probably get to a non-unique solution. But how much of the time scale is going to shift in that, it's probably not going to be dramatic.
Okay, so you're saying that if you did just a one-stage model at a constant decompression rate, you couldn't reproduce the H2 out and the CO2 rate?
No, you can't.
Yeah.
So that's where the best fit feature really
so
helps.
yeah.
Is essentially you can try, but if you can't do it, you can't do it, and so you need to then lower the concentrations.
Yeah.
And yeah.
You also have a texture argument because the higher concentration are in the inclusions,
Yes.
which were formed before.
Yes. Oh, you mean like they might never go back to those original concentrations?
Because your re-entrance or whatever is a melt inclusion not yet formed.
Yeah. No, it's true. But, so, I mean, the melt inclusions are essentially giving us where we think everything started. And then the reentrant is doing other things.
Later part of the story.
Yeah. No, it is. I mean, using them together allows us to, I think, get at different time frames in this eruption, which is really nice.
What's the problem with the Humphreys paper?
With the what?
The paper?
Oh, so they did grayscale calibration of those profiles, and so the Lloyd et al. Paper in 2014 discusses in depth about how other elements could be affecting that grayscale calibration, so it's not just water that they're getting this gradient for. So that was mostly the argument, and they're very fast. They're faster than any other method has given, and faster than conduit models, and it's the only system where that happened. So I think that was the argument, essentially.
D'autres questions?
No. 100 meters a second is
Merci Madison.